So welcome everyone to our STAMPS webinar series. It's a pleasure to introduce Parker Holzer from the Department of Statistics and Data Science at Yale University. So as you may know, our original scheduled speaker couldn't make it today, but we are delighted to have Parker step in at a really short notice and give a webinar. Still on the same topic of statistics for exoplanet detection. So Parker is currently a PhD student at the Department of Statistics and Data Science at Yale University. He got his undergraduate degree at the University of Utah as a double major in mathematics and applied physics, which, by the way, fits perfectly with the interdisciplinary spirit of STAMPS. So Parker's research primarily centers on applying statistics to astronomy, with a current focus on exoplanet detection. So Parker, maybe you can take it from here. So
Great.
I'm going to see if I can pin your video.
Okay, cool. Thank you so much. Let me go ahead and share. So thank you for that introduction, and I feel very privileged to have this opportunity to present my research. Yeah, even though it was last minute, I'm very glad to be able to present this. I'll mainly be talking about discovering exoplanets with Hermite-Gaussian linear regression. I'll give some more details of that, of course. But basically, it's looking for ways to improve the methods used to detect planets that orbit distant stars. Those I'll refer to as exoplanets throughout this presentation. And the general idea of why there could be some improvements here is because the signal for detecting exoplanets is often very small. And on top of that, there are other signals that can interfere with the signal we're looking for. And so this is a very general idea that probably ranges across a lot of different fields of how to disentangle really small signals. And so this is one application of that. So,
Parker, can I just very quickly ask, if you can do a full screen, is that possible? Yeah, excellent.
yes. Okay,
perfect.
cool.
Thank you.
Yes, thank you. Yes, okay, cool. So this is work that I've done in collaboration with Jesse Czeski-Kay, who I know many of you know, and that's great. And I also worked with astronomers Deborah Fisher and Lily Zhao at Yale University, and these three have been a lot of really good help to me in this research, and so I owe a lot of the credit of this research to them. And so let me give an overview of the general idea of what I've been working on. So there are a number of ways that people have used to try and find exoplanets, and the probably most historic one is called the radial velocity method. This was the original way that people started looking for exoplanets back in the 90s or so. That's when it started kind of really taking off. And the general idea behind this radial velocity method is that if you have a planet orbiting a distant star, then the gravitational pull of that exoplanet will cause the star to wobble back and forth. Sometimes it'll be coming towards us, and sometimes it'll be going away from us. And that would manifest itself in the light of the star by rescaling the light's wavelength. If it's coming towards us, it would rescale the wavelength to be slightly smaller or bluer. And if it's going away from us, it would rescale the light to be slightly redder or have a slightly higher wavelength. And this is called a Doppler shift, for those of you who've heard of that before. And so, if we look at a star and we find that its light is having a rescaling of the wavelength over time, and that it's oscillating back and forth, then presumably that is evidence that there is an orbiting exoplanet around that star. And as you might imagine, most planet-star systems have the planet with a much smaller mass than the star. At least that's especially the case with the Earth and the Sun. And so this wobble in the star is often very small. So that's the reason why the signal is very small. But yeah, the general approach of the radial velocity method is to separate it into two main steps. The first step is to observe a star a number of times, and from the light of that star, detect a Doppler shift, and from that infer a particular radial velocity. And then, after you've observed that star a number of times and got an estimated radial velocity at each of those times, you fit what's called an RV curve, a radial velocity curve, over time. And oftentimes that just is something similar to a sine curve. Or if there's some really strong eccentricity in the orbit of the planet, it can look a little bit different, but you can think of it as a sine curve, basically. And this is the radial velocity method. Now, I mentioned that the data that we use in the radial velocity method is the light from the star. More particularly, it's referred to as a stellar spectrum. And this is a picture of a stellar spectrum for the star 51 Pegasi as collected by the Express team at Yale. And what a spectrum is the wavelength of the light from the star, shown on the horizontal axis, and typical spectra have thousands of angstroms of wavelength, and here I'm only showing 10 just for the presentation. And on the vertical axis, we have what I've called normalized flux here. You can think about it as a measure of the brightness of the light, at least the relative brightness of the light, as a function of wavelength. And what you'll notice when you look at this or most spectra is that you have these narrow dips in relative brightness. And these are referred to as absorption features. And these absorption features are key to discovering or detecting a Doppler shift in this spectrum, because a Doppler shift would rescale this wavelength axis, and therefore, over time, if there's an orbiting planet, you would see these absorption features shifting right and left over time. Now, it's a little bit of a stretch to say you would see that shift, because the signal is so small that if you were looking for that signal by eye, you simply would not be able to see it. It is so small that we basically have to rely on mathematical and statistical tools to detect that signal. But at least a shift in a multiplicative manner of these absorption features is the signal we're trying to get out of these stellar spectra. And so how do we detect that signal in the spectra? Well, there have been a number of techniques developed, some of which have been around for decades, others of which are kind of a little more new. But the one that's been around the longest, and that's, as far as I'm aware, still the most commonly used technique, is called the cross-correlation function. And the way this works is if you have a spectrum of a star, represented by these dotted lines here, and if you take what's often referred to as a mask, and you Doppler shift that mask at various proposed radial velocities, and at each of those, calculate the area underneath the spectrum by usually calculating a dot product or something like that, then you can basically look for where that area, which is represented by the value of the cross-correlation function, where that is minimized. And the radial velocity that it's minimized at would be your estimated radial velocity. And that's the basic idea of the cross-correlation function. There are, of course, ways to generalize this so that your mask is maybe not just boxcars, so that it's more general shapes, or you add more weight to certain absorption features that you trust more than others, but they all kind of focus on this same idea. And there are other techniques as well, a good amount of which are actually based on the cross-correlation function. And these are some of the techniques that have been developed. The CCF is the most common. And so that's what I'll be comparing to with a new approach that I'll introduce for this purpose. Now, I mentioned these have been around for a while, many decades, and you've probably heard in the news of exoplanets being discovered. At least I hear about that in the news all the time, and maybe that's because Google spies on me and sends me stuff that I look for a lot, but maybe you've heard of it too. And this plot right here basically represents a distribution of the discovered exoplanets through this radial velocity method. On this horizontal axis, this is the period of the exoplanet's orbit, or how long it takes to go around its star. And on this vertical axis is the velocity amplitude, or the maximum radial velocity that that exoplanet imposes on its star. And these two basically help to characterize most exoplanets. And you can see that there have been a lot, at least as far as March earlier this year. And that's great. But when you look at where the Earth would lie on this planet, down here at about 365 days and about 10 centimeters per second, you see that there is an obvious gap here, that we really haven't gotten to Earth-like exoplanets around Sun-like stars. And there are multiple reasons for this, and that's why it's still a focus in the astronomy community. Some of the reasons for this is because, well, the signal for an Earth-like planet around a Sun-like star is really small. The signal's really small for almost all of these exoplanets that have been discovered, but it's particularly small for Earth-like exoplanets. But there's another underlying issue that's also at play, and that's stellar activity. And what I mean by stellar activity is stuff going on in the star itself. A star isn't just a solid bowling ball floating out in space. There's stuff going on in the atmosphere of the star and around the star in the form of star spots or facula or granulation, or there are probably a number of other forms of stellar activity that you can think of. And this comes back to bite us because these can actually mimic the signal of exoplanets. And at least they can cause more noise to be in the signal. So unfortunately, if we're not careful, we might find that some of the exoplanets we think we discover are false positives that if we observe the star 20 years later, are not reproducible. And so we need to be very careful about this stellar activity signal. And when you get down to the level of Earth-like exoplanets, that becomes very difficult to do. What makes it even more of a challenge is that stellar activity does not really have a very well-known and accurate enough physical model. And so we don't really know exactly what the signal of stellar activity is. We know that it is kind of similar to the signal of a Doppler shift, but we don't know much about how it's different. Fortunately, with this paper, Davis et al. 2017, they helped to show that there actually does exist a detectable difference between the signal of stellar activity and a Doppler shift. So that's good. It it gives us a little bit of hope that we can find a way to disentangle these two. And this is basically one of the main sources that we need to figure out how to solve before we can really start discovering Earth-like exoplanets around sun-like stars. So before I go on, are there any questions that anyone has about this so far?
Yeah, I have a quick question. So you showed the current state of discovered exoplanets. So how far away can we detect exoplanets? Just
like how far away in space?
yes, from here, from Earth.
That's a good question. It basically depends on how bright the star is you're looking at. If you have a star that's really, really close but very dim, then there's not much hope in discovering something. But if it's on the other side of the galaxy and if it's really bright, you might also have a tough time doing it. But as far as what the distribution is for distances to discovered exoplanets, I'm actually not sure. But at least I know that they're all within the Milky Way galaxy.
Okay, thanks.
Yeah. So this has been on people's radar, this idea to try and disentangle stellar activity from the signal we're really after for a while. And there are generally two types of attempts that have been made so far. One of them takes place in the step where we actually estimate the radial velocity from the spectra itself. And a lot of these studies do something along the lines of trying to detect and remove absorption features that are sensitive to stellar activity. Unfortunately, a recent study shows that that might face some difficulties because at least 89% of absorption features are sensitive to stellar activity. So that might be a particularly difficult thing to do. But other people have said, okay, let's just estimate the radial velocities the same way we've always been doing them with the traditional cross-correlation function. And let's try to model out the effect of stellar activity when we fit the RV curve, when we deal with the time series of the radial velocities. And as an extra helper, let's use some other statistics, like that are often called stellar activity indicators, to try and disentangle those two signals. And this is essentially what David Jones and some other people have been working on with Gaussian processes. And so it's a very similar issue, but yeah, we're basically working on the same problem overall. My research, however, is over here in this category, and it basically comes down to the idea that the cross-correlation function is a little complicated. And it's complicated in the sense that you can't write down the estimator for the radial velocity in closed form. And therefore, it's a little bit difficult to extend for the purpose of disentangling stellar activity. And so my research is developing a new way to get an estimate of the radial velocity from the spectrum in a way that's designed to be easily extendable with statistical methods. And so ideally, my approach and the approach from David Jones and the others over here would be able to both be used to get at this stellar activity signal. So let me introduce you to this new method that helps to detect a radial velocity in the spectrum. It's called the Hermite-Gaussian radial velocity method, HGRV for short. And at a glance, it's basically just assuming that the true velocity is small, and that's almost always true for exoplanets. And we want to estimate that velocity with weighted simple linear regression of what's called the difference flux on a sum of first-degree Hermite-Gaussian functions. By difference flux, I mean the flux that we actually observe from a star, which is represented in red in this plot, minus what I call the flux of the template spectrum. And that is represented in dashed blue here. And the template spectrum is nothing more than a quiet spectrum. By quiet, I mean there's no stellar activity, there's no Doppler shift, and there's no noise. And this, while we don't have access to the true template spectrum of a star, we can at least estimate it pretty accurately through nonparametric smoothing. And so the difference flux is just red minus blue in this plot. And the difference flux is plotted down here. And to the naked eye, it looks like nothing more than just noise. And that's because of how small the signal is. If it were a large signal, you would see an obvious shift between the red and the blue. And you'd see very obvious shapes here instead of just almost noise left in here. And again, this is only about 5 or 6 angstroms of wavelength out of the thousands that we have. And it's because we have so much more than just this that we can actually detect a signal from what locally looks like just noise. And this signal is pulled out through just simple linear regression with this new approach. So let me give you a few more details behind this HGRV approach. I first need to define a few things. The first thing to define is, of course, the Hermite-Gaussian functions. These are nothing more than just a Hermite polynomial multiplied by a Gaussian and normalized so that they form a basis for square integrable functions. And what they look like is represented in this plot. These Hermite-Gaussian functions have a general center mu and spread sigma, but I've set those to be 0 and 1 here respectively. And the 0th degree Hermite-Gaussian function is nothing more than just a Gaussian. And the 1st degree Hermite-Gaussian function, which is the one that's relevant for this method, is in dashed orange here. And these are the Hermite-Gaussian functions that we use. And of course, as you get to higher and higher degrees, they get more and more complicated. I also need to define some other things like what I've called standardized approximation error here. And there's a theorem that quantifies some things, but I'll save you some time and just state what this theorem means in the context of exoplanet detection. It basically means that at small radial velocities, which is true for most exoplanets, the difference between a Gaussian, which is representing absorption features here, and a Doppler shift of that Gaussian can be well approximated as a constant multiple of the 1st degree Hermite-Gaussian function. And this isn't too much of a surprise if you think about it, because the derivative of a Gaussian is a constant multiple of the 1st degree Hermite-Gaussian function. And while I mentioned that a Doppler shift is a rescaling of the wavelength axis, as long as you're dealing with a narrow window of wavelength and are far away from 0, that rescaling is almost the same thing as an additive shift. And if it's an additive shift, then a small shift is well represented by a constant multiple of the derivative. So this isn't too much of a surprise when you start to think about it. And overall, that theorem means that we can use this linear model. We can take the difference flux that I introduced before, which is yi here, and we can take the wavelength of the spectrum, which is represented by x here, and then we can look at a number of other things that go into transforming that wavelength, such as the 1st degree Hermite-Gaussian function, some other parameters here that are well estimated from the template spectrum, and summing across absorption features, and we're able to create a variable that is linear with respect to the difference flux.
Parker, I see a question here in the chat box. So David Corliss is wondering, would it be true that if this approximation did not hold true, it would be because the signal is very large and therefore we wouldn't need to use these methods in the first place?
Yes, that is a great question. Yeah, this is a method that's particularly designed for small exoplanet signals. If we were to try and use this method for detecting a large radial velocity, such as that would result from the Earth's motion around the sun, or other things like binary systems, we'd very likely get a very poor estimate. So that is good to point out that this is particularly built for small radial velocities. So yeah, let me break apart this HGRV linear model into a few different pieces. The first piece is, like I mentioned, just a first-degree Hermite-Gaussian function centered at the wavelength mu j. And in red, this is just a relative amplitude of that absorption feature. And then in green, this is just a sum across the m absorption features in the spectrum. And so if you look at this plot right here, you've got in dashed red this variable. It's a sum of first-degree Hermite-Gaussian functions, each with its own relative amplitude. And this is the explanatory variable, you might say, that makes the relationship linear with respect to the difference flux that's plotted in blue here. And again, this looks like just noise to the naked eye. And the great thing is that the coefficient of that linearity is the radial velocity that we intend to estimate. And so, long story short, this is simple linear regression. In fact, it's actually simpler than simple linear regression because there's no intercept. And as far as the noise, we allow it to be heteroscedastic normal, and it actually turns out that because of the nature of the noise, the variance is actually pretty easy to estimate. And there are other values to why a linear model is good for this, but the one that I'll mention here is that this is one of the most easily extendable statistical models that we have out there. And that makes it particularly good because we know we're going to need to extend it for stellar activity. So that's one of the great values of this model. Not only can you write down the estimator in closed form, but you can extend this method for future purposes. So let me walk you through this whole process of this HGRV method. There are a few steps that I haven't mentioned yet, or at least I've kind of brushed over so far. So let me walk you through it from beginning to end. The first step is, after you've collected all of the spectra from the star, each at a different time, and each with a different radial velocity, the first thing to do is to estimate that template spectrum. And we do that by just stacking all of these observed spectra together and just applying local quadratic regression. Of course, there's nothing particularly important about using local quadratic regression here. You could use pretty much any other non-parametric smoothing, and you'd probably get a good estimate of the template spectrum. And in this plot, just as a side note, with all of the observed spectra plotted in gray, it gives you an idea of the level of noise that is in the spectrum. And in dashed red is the estimated template. So it works really well. And this is for applying the method to 56 observed spectra for the star 51 Pegasi. This is the star that is famous for essentially kicking off the search for Earth-like exoplanets around Sun-like stars back in the 90s. So that's step one, to estimate the template. step 2 is, well, we know we're going to need to find absorption features sooner than later. And so that's the next step. Take this estimated template and apply some algorithm. We have an algorithm in the paper that this talk is based on called Absorption Feature Finder that searches for absorption features. And those are plotted in the horizontal blue here, the windows of absorption features given by this algorithm. The estimated template is in solid red, by the way. And once we've gotten those absorption features, we can estimate those extra parameters that I mentioned earlier that are essentially just the fit parameters for fitting a Gaussian to each of these absorption features. That's one of the assumptions of this method, that absorption features are approximately Gaussian shaped. And in reality, if you look at the physical models, you'll find that that's basically never exactly true. But if you look at the fitted Gaussian spectrum in dashed blue here, you'll see that it actually does a pretty good job of approximating the template spectrum. So it's never exactly true that they're Gaussian shaped, but it sure is close. So that's step 3, just fit Gaussians to all of these features and get these extra parameters. And you only need to do this once for a given star. And then the last step is just to apply this linear regression at each particular time, using the same template spectrum for every time. And I kind of brushed over this earlier, but we not only estimate the radial velocity by running simple linear regression of the difference flux on this new variable, but it's also very easy to get its uncertainty. That's not quite true for some of the other methods. Of course, there are ways that the uncertainty is estimated, but most astronomers have admitted that they don't really trust the uncertainty that they get for the radial velocities. But this, we all know how to get the uncertainty of a coefficient in linear regression. And so this is the overall method. Are there any questions about it before I move on?
Hey, Parker.
Yeah.
This is Colin Polich from CMU. I have one question backing up to step 1.
Mm-hmm.
So fitting your template, your example here is 51 peg, and so it's the most famous, exoplanet example. And I think you said you have 56 observations of the spectrum here, which I agree. It totally makes it pretty much irrelevant which non-parametric method you use to smooth 51 stacked spectra here. But I'm wondering, this is not an area I work in, so this is a naive question. In more typical examples, how many stacked spectra do you have? Because it seems to me that if you only have very few, then it could start to make a difference if you're using, say, linear versus non-linear smoothers, in this case, where you expect a signal that has abrupt dips in it.
Yeah, that's a good point. Yeah, at least through simulation in the paper that this talk is based on, that's uploaded to the archive in case you're interested, we have found that once you get above about 20 observed spectra, which is actually a very typical number, there's not much improvement made, at least with this one local quadratic regression. But we actually haven't tried out other smoothing methods. And you're right that our estimate might not be as good down here at this really deep line as it is out here at this very shallow flat part. So there might be room for improvement here. So that's good. That's a good thing to mention.
Okay, thanks.
Yeah, great question. Any other questions at all?
This is David Rupert at Cornell. So it would seem to me that when you have those troughs there, those sharp downward parts, that if you wanted to estimate that accurately, that you would want to have a bandwidth that is local rather than global.
Mhm.
Whereas the same bandwidth is not going to work well in a flat spot, or where there's a small dip compared to a large dip. So are you using a global or a local bandwidth?
Oh, that's a good question. Kind of both. Because in practice, we don't fit the whole thousands of angstroms worth of the spectrum simultaneously. And since some parts of the spectrum have more absorption features than others, we only fit 5 angstroms at a time. But for that 5 angstroms, we use a constant bandwidth. So for this plot right here, this all used the same bandwidth, but we allow that to be different for every 5 angstroms. So I think what you're aiming for is it's a constant bandwidth, and yeah, it would be probably a good thing to branch out to not having a constant bandwidth.
That would be useful to plot with 2 different bandwidths and see where the bandwidth had a big effect.
Yeah. We did find that when we do pick a bandwidth through generalized cross-validation, that it's actually pretty flexible. You can actually take a pretty good range, and the generalized cross-validation is pretty flat near that bottom. So it does seem to be that it's not too sensitive to that. But again, that's kind of fitting the deep lines at the same time as these shallow parts. So yeah, good question. Okay, so how did this application to 51 Pegasi work? Well, here are the results for it. I mentioned how after we estimate the radial velocity at each time, we still need to fit an RV curve to it, which, since 51 Pegasi is known to have basically no eccentricity, or at least a very tiny eccentricity, we just fit a sine curve here. And that gave some fit parameters here that helped to describe the planet. And they line up with current studies, or previous studies of 51 Pegasi. Here is the RV curve fitted to the estimated radial velocities at each of the times. You can see how it's a very good fit overall. And if you calculate the scatter about this RV curve, you get an RMS of 0.774 meters per second. And if we compare this to what we get when the radial velocity methods, or the radial velocities, are estimated with other methods, such as the cross-correlation function or this more modern forward modeling approach, we find that the scatter is larger for these other approaches. And so this is suggesting that not only is the HGRV method likely to be very easily extended for stellar activity, but just from a modeling perspective itself, it seems to be, it seems to have lower risk, at least from this applied data set. And so we analyzed this a little bit further through simulation, of course. And so by analyzing the risk of this method and comparing it to the cross-correlation function, we get the results shown in this plot here. We tried it out for a variety of noise levels that pretty much all cover the typical signal-to-noise ratios that you get with spectra nowadays, and for a variety of true radial velocities, ranging from 0.01 meters per second all the way up to 100 meters per second. And an Earth-like exoplanet would be down here at about 0.1. And most of the exoplanets that have been discovered are well within this range. And if we look at each of the pairs of radial velocity and signal to noise, if we look at the difference between the root mean square, or the square root of the mean squared error, between the two methods, we find that the difference is negative, or in other words, the HGRV has a smaller RMS. They're all negative in here. And so this is kind of backing up the idea that the HGRV method seems to have lower risk than the traditional CCF approach. And what's probably more interesting is when we break up this mean squared error into its different parts of bias and variance. This plot right here essentially represents the difference in the standard deviation between the two methods. It's again very much negative, meaning that the HGRV has smaller standard deviation than the CCF method. But at the same time, looking at the differences in absolute bias, we find that depending on what the underlying signal is, the HGRV method has a little bit more bias in it. At least that becomes pretty obvious at high radial velocities. And this is interesting because this is kind of the same thing as Stein's phenomenon, where a slight increase in the bias leads to an overall reduction of the mean squared error. And that's always fascinating for me to think about. And where is this bias coming from? Well, at least two of the possible sources of this bias would be the assumption that the absorption features are Gaussian shaped. I mentioned how that's never really exactly true. And that might have something to do with some of the bias that's in there. It also might be the case that fitting or treating a Doppler shift as an additive shift has something to do with this too, because in reality, it's a rescaling or a multiplicative shift of the wavelength. Whereas since we're using the derivative, it's kind of treating it as an additive shift, locally at least. So any questions about these simulation studies at all? Okay, so just as an extra note, this reduction in mean squared error was kind of a little bit of an extra cherry on top, but it wasn't exactly the main motivation behind this method. The main motivation was to be able to extend it for stellar activity, which we're still working on. And there are a couple different ways that you could extend this method, probably more that we haven't thought of, but at least one way is to include more than just one of those Hermite-Gaussian functions in the linear model. Include some of the higher degree ones as well. And since only one of those should be affected by a Doppler shift, we can try and indicate the presence of stellar activity by running an F-test on all of these other additional variables that we might add in. This is something that we're working on and that seems to be showing some good promise so far. That's kind of a first step where we just indicate the presence of stellar activity but haven't done anything to try and model it out. It gets a lot more complicated to try and model it out. But there are ways to do this by, well, one possible way that we've been trying out that definitely still needs some details worked out is, well, we can introduce a new variable into the regression that's orthogonal to this Doppler variable, and thereby would not be affected by a true Doppler shift. And so we can conclude that the only thing that would influence that one variable would be stellar activity, and that might help us model it out. So, just in conclusion, we have found that this radial velocity method for finding exoplanets can be formulated in simple weighted linear regression. Weighted because I mentioned that the noise is often heteroscedastic. And we do so by using these generalized Hermite-Gaussian functions. And as a great cherry on top, we find that when we do that, it has smaller risk than the traditional CCF approach, at least in the simulation study we've looked at and in the 51 Pegasi data that we've considered. And this is all based on a paper that's been uploaded to the archive. It's still in review, but the methodology has been implemented in the R package, RV method. It's publicly available, and you can also find Python code that implements it as well on this publicly available GitHub. And so just in closing, these are the references, and I'd be happy to take any questions that you have.
Yeah, Parker, it's Anne. I have a very basic question about exoplanet detection.
Mm-hmm.
So in the beginning, you talked about different radial velocity method techniques.
Mm-hmm.
And I've heard some talks on exoplanet detection using, I think it's like transit methods. And I was just wondering when, what the differences are and what kind of problems you look at.
Yeah, good question. So yeah, there's the radial velocity method that I've described, and then there's other things like the transit method. The transit method is a little bit different in that it is not looking for a Doppler shift in the light from the star, but instead looking for a little bit of a shadow, or the brightness of the light taking a small periodic dip because of an exoplanet crossing in front of it. That is also a very productive way of looking for exoplanets. It hasn't replaced the radial velocity method because, unfortunately, the transit method assumes something about the orientation of the planet-star system. It assumes that the planet is orbiting the star approximately in the same plane that, that we lie in when observing the star. The radial velocity method kind of assumes that too, but is much more flexible. You don't need to have the planet oriented in the direction that it would cross right in front of the star for the radial velocity method to work. But yeah, there is that other signal that could be studied as well. And oftentimes both the transit and the radial velocity method are used to confirm the existence of exoplanets.
So it's mainly that it has more assumptions, or do you look at different kinds of problems?
Yeah, they kind of have different assumptions. I mean, they're similar in the sense that they're ideal when the exoplanet is oriented in the right way in its orbit, kind of like right in front of the star from our perspective. But that assumption is more strict for the transit method than it is for the radial velocity method. And that being said, the signal from the transit method is often a little bit more obvious from what I've heard than the radial velocity. So there are pros and cons to both.
Okay, thanks. I see we have a hand raise here. Also, Kevin Stassen.
Hello, great presentation. This is Kevon Stassen at Vanderbilt. Following up on the last question about the transit method, one of the ways that we often find additional planets in systems where a transiting planet is already known is to look for shifting in time of the known transit, what we call transit timing variations. And I wonder if you could represent a transit in a star's light curve with a Gaussian. I'm assuming that that's what you would need to do. Could you basically apply the same technique and look for small shifts in time of the transits as a way of detecting additional bodies in the system?
That's a good question. Yeah, I don't know. At least from what I've seen from transit curves, they don't look quite Gaussian, but that's okay. We could take whatever shape they are and approximate the derivative of that. But yeah, so I think there is a way to kind of apply this idea to those transit curves as well. Of course, it might be a little bit tough depending on how high the noise is for a transit curve, because here we've got thousands of angstroms that results in often hundreds or thousands of absorption features in a single spectrum, whereas there's only one of those for every time the planet orbits its star. So that might be a little bit of a difficulty.
I see. Okay, thank you.
Yeah, thanks. I see Eric Feigelson also has a question.
Hi there, Eric Feigelson from Penn State. Thank you, Parker, for interesting talk. I also want to ask a question that's not directly on your work, but sort of around it. So you have a promising method for, in astronomy terms, of reducing the error bars on the true stellar radial velocity, and therefore giving more promise of getting sub-meter per second detection, which is smaller planets through radial velocities, which is urgently needed. My question is that let's just assume that you succeed and get a factor of 2 or 3 smaller error bars. We're still left with the problem of having a very sparse irregular time series, typically a couple dozen points, maybe a few dozen in the good cases, a couple dozen points, and we're looking then for a periodicity. And in this case, it's not even a sinusoidal periodicity necessarily. It could easily be a elliptical orbit. And so I was wondering, what is your preferred method for the second stage of the sparse irregular time series periodicity problem? Or you just don't have an interest in that? Or
Oh, I definitely have an interest in that, yeah. That's a good question. Currently, I would default to the method that has been recently developed and that David Jones would have presented today had he been able to make it. But at the same time, that's something that we're working on as well. Is there a way to merge these 2 steps of detecting the radial velocity and fitting an RV curve simultaneously? And there's still some details to work out, but I would default to this Gaussian process method that David Jones and the others have developed.
Okay, thanks very much.
Yeah.
So Parker, can I ask a question? This is Mikael. I cannot raise a hand because I'm the host. So in one of your slides, you mentioned this forward modeling approach, and you compared that to your approach. I was just wondering if you can say a few words about what that method does. And I realize it's not your method, so if you're not very familiar with it, that's okay. But if you happen to know how that works, I would be curious to hear a bit about that.
Yeah. So fortunately, I know a decent amount about what the forward modeling approach is. I don't know all the details, but it was developed by people who I collaborate with a lot. So the general idea is that it's basically the cross-correlation function, except that it's trying to, it basically tries to throw out absorption features that are sensitive to stellar activity. But other than that, it's almost the same thing as the cross-correlation function. So that's why it's not, in this case, there's not too much of a difference in the RMS for these 2. And I can only assume that it's basically because they're both using the cross-correlation function. This one is able to eliminate some of the noise, but it's still kind of based on the cross-correlation function.
Could I just chime in a little bit? I think also with the forward modeling, they're doing the cross-correlation function idea, but using a template spectrum and using it on 2 angstrom sections of the spectrum.
Yeah.
And then they combine the estimated RVs from those 2 angstrom sections and to have a way of then estimating an overall RV. So it gets into a little bit more detail of the spectrum and adapts more to the shapes of lines.
Cool, thank you.